The gold in your wedding ring was forged in a collision so violent it bent space-time. Two dead stars smashed together at a third the speed of light, stacking more neutrons in one place than physics thought was possible. That single event created every atom of gold on Earth. This video follows one question to its breaking point. How many neutrons can you stack before the universe refuses? We will start with a single particle, descend through nuclear pasta stronger than steel, cross a quantum wall holding back the weight of a dead star, and arrive at the moment reality collapses. Subscribe if you want to see it through. Prepare yourselves. We begin. The ring on your finger, if you happen to be wearing one, was forged in the most violent event the universe knows how to produce. Forget supernovae. Forget asteroid collisions. The gold inside that ring required something far stranger, something that forced the universe to work right at the edge of its own rules just to keep going. Gold is made of atoms, and at the center of every gold atom sits a nucleus packed with protons and neutrons. The protons are what make gold gold, but the neutrons are the real story. And that story begins with a problem. Gold cannot form inside a dying star. That surprises most people. Stars are famous for building elements, fusing hydrogen into helium, helium into carbon, carbon through heavier and heavier elements all the way to iron. But iron is the wall. Fuse iron and you absorb energy rather than release it. The star has nowhere to go. So everything you see on Earth that is heavier than iron, all the gold, all the platinum, all the uranium, had to come from somewhere else. And the conditions required to make it are so extreme that only one event in the observable universe can produce them. Two stellar corpses. Two dead stars denser than anything else in existence, circling each other for billions of years, losing energy through gravitational radiation, spiraling inward centimeter by centimeter across geological timescales. Then, in a fraction of a second, they collide at roughly a third the speed of light. The flash outshines their entire galaxy. A cloud of glowing material expands outward at a significant fraction of the speed of light, and inside that cloud, an unimaginable crush of neutrons piles together faster than any force in nature normally allows. That frenzied, neutron-saturated moment is where your ring came from. Here is the question this video follows from its very first frame all the way to its last. How many neutrons can you stack in one place before the universe refuses? Is there a limit? Where is it? And what happens the instant you cross it? To find out, we start with a single neutron floating alone in empty space, and we count our way up through nuclei, through the edges of the periodic table, through the interior of a star made almost entirely of neutrons, right up to the moment the whole structure collapses. The answer involves one of the strangest menus you have ever seen, a quantum wall that fights gravity itself, and a number so large that writing it out requires more digits than there are atoms in your body. The atoms in your ring are the direct product of physics working as close to its own breaking point as nature allows. To understand how, we have to start with a single particle, the one most people have never truly stopped to think about. Strip away everything from an atom. Remove the electrons spiraling at the edges. Set aside the protons at the center. What you are left with is the neutron. And the first thing to understand about it is that it seems completely unremarkable. The neutron is electrically neutral, completely invisible to the electromagnetic force. Every charged particle in the universe announces itself constantly, leaving trails in detectors, bending in magnetic fields, interacting with everything it touches. The neutron does none of that. Pass one through a wall, and it moves through without disturbing a single electron. Send it through an entire room, and you would have almost no way to know it was there. A ghost particle, slipping through matter as though matter were barely a suggestion. And yet it is one of the things holding the universe together. Every atom heavier than hydrogen has neutrons packed into its nucleus alongside protons. Carbon, oxygen, iron. Gold. Every element you have ever touched contains neutrons at its core. Those neutrons are the glue. Without them, proton-only nuclei would fly apart instantly, pushed outward by the electric repulsion between their positive charges. Neutrons dilute that repulsion and allow the nucleus to hold. Look closer, though, and the unremarkable description completely dissolves. Inside a neutron, 3 quarks are bound together by the strongest force in the universe. 1 up quark and 2 down quarks, each carrying a fractional electric charge that sums to exactly 0. The force binding them, the strong nuclear force, grows more powerful the farther apart the quarks drift, like a rubber band that resists harder the more you pull. This is why quarks are never found alone. They are permanently locked inside particles, invisible, never escaping. Even though the neutron is electrically neutral overall, it carries a small magnetic moment pointing in the wrong direction for a featureless neutral sphere. Something inside is creating that magnetism. That something is the quark arrangement, a hidden fingerprint of the particle's true nature. Here is the detail that will matter enormously later in this story. The neutron is fractionally heavier than the proton, only by 1 part in 1,000. That gap sounds irrelevant. Because of it, however, a free neutron will always tend to convert into a proton if given the opportunity. At nuclear scales, that tendency is suppressed. At stellar scales, it shapes the fate of objects more massive than the star that holds this planet in orbit. The neutron weighs just a fraction more, and that fraction changes the universe. There is one more thing. Protons left alone in empty space remain protons for far longer than the current age of the universe. The neutron is different. The neutron has a clock, and when you first hear how short that clock runs, the number is shocking. Free a neutron from its nucleus, let it drift alone in space, and you have about 14.5 minutes before it destroys itself. 14 minutes, and then it is gone. In that window, one of the down quarks inside the neutron flips into an up quark through the weak nuclear force. A burst of energy is released. The neutron becomes a proton. An electron flies out. An antineutrino streaks away at nearly the speed of light. The neutron is gone. The process is quiet, almost gentle, and completely irreversible. This is beta decay, and the timescale is what makes it genuinely strange. 14 minutes is nothing in cosmic terms. Light from the nearest star beyond our own takes more than 4 years to reach us. A neutron flying freely through space would be dead long before it traveled even a fraction of that distance. If you fired a beam of neutrons across a very long hallway, a significant fraction would decay before reaching the far wall. You might wonder how this matters for stacking neutrons in enormous quantities. If they die so quickly, how can you accumulate enough to build anything interesting? The answer is coming, and it is one of the most elegant results in quantum mechanics. But first, there is a mystery buried in this decay that physicists have spent decades trying to resolve. Measuring the neutron's lifetime turns out to be extraordinarily difficult, and 2 different experimental methods disagree. In one approach, researchers trap ultra-cold neutrons in a magnetic bottle and count how many survive over time. That method gives a lifetime of about 878 seconds. In a second approach, they fire a beam of neutrons and count how many protons appear from decays along the way. That method gives roughly 888 seconds, 10 seconds apart. At the scale of particle physics, 10 seconds is a canyon. The discrepancy has persisted for decades. It might be a systematic measurement error in one of the 2 methods. Or, according to some theorists, it might hint at unknown physics, a fraction of the neutrons decaying into a particle that the bottle experiment cannot detect, something lurking in the decay channel that has never been directly seen. A team in Japan recently produced a beam result that came in closer to the bottle value than any previous beam experiment, tightening the gap slightly. Whether the mystery is resolving or deepening is still genuinely open. But here is the thing that upends the whole picture. Trap a neutron inside a nucleus, and the 14-minute clock stops completely. A neutron locked inside a carbon nucleus will be there in 1 trillion years. Lock it inside, lead, and it will outlast the heat death of the universe. The same particle with a 14-minute expiration date becomes effectively immortal. The reason why is one of the most important ideas in this entire story, and it is the same force that will, much later, hold up a dead star against gravity. Inside a nucleus, the neutron cannot decay, and the reason is pure quantum mechanics. Beta decay requires the neutron to become a proton. For that conversion to happen, there must be an available quantum state for the new proton to land in. Every particle in quantum mechanics follows a strict layering system, energy levels arranged like the rungs of a ladder, each rung able to hold a limited number of particles. In a nucleus with the right number of protons, all the low-energy proton rungs are already occupied. The proton that the decaying neutron would become has nowhere to go. This is the Pauli exclusion principle doing its first great job. Wolfgang Pauli established it in 1925 while working out why electrons in atoms do not all collapse into the lowest available state. The rule is absolute. No two identical fermions can share the same quantum state. Fermions are particles with half-integer spin, including electrons, protons, neutrons, and quarks. The rule does not bend. It is a hard mathematical wall built into the structure of the universe. Because all the low-energy proton states in a stable nucleus are already filled, the neutron has nowhere to send its decay product. The conversion is energetically blocked. The 14-minute clock has no mechanism to run. There is a second, deeper reason the neutron is stable inside a nucleus, visible in something you can physically measure. Every nucleus is slightly lighter than the sum of its separate parts. Take 12 protons and 12 neutrons, weigh each one individually, add those weights up, and the total is slightly higher than the weight of a carbon-12 nucleus. Where did that mass go? It became the binding energy holding the nucleus together. Mass and energy are equivalent, and the energy cost of ripping a nucleus apart is stored as the mass difference between the intact nucleus and its individual components. That missing mass is the glue. It is real, measurable, and it means that staying bound inside the nucleus is energetically favorable. Together, these two effects turn a particle with a 14-minute lifespan into one that lasts effectively forever. The same neutron that decays in an empty hallway is immortal in an atom. Now push further. If neutrons become stable when surrounded by the right nuclear environment, and if that stability depends on energy levels being filled, then stacking more and more neutrons into a nucleus must have limits. At some point, the energy rungs run out. At some point, the structure starts to resist. The answer requires understanding something deeper about why neutrons need partners at all. Two neutrons in empty space cannot form a bound pair. The strong nuclear force acts between them. The attraction is genuinely present. The force is real. But it is not enough. The di-neutron, as physicists call this hypothetical two-neutron system, is unbound. Two neutrons placed close together will simply drift apart because the quantum mechanics of identical fermions creates an energy cost that the nuclear force cannot overcome. Place a proton into the picture, and suddenly the nuclear force has room to work. The simplest bound nucleus that exists is the deuteron, one proton plus one neutron, barely stable but unmistakably real. This is the first surprise in the stacking problem. Neutrons require partners. As you build heavier nuclei, the partnership requirement becomes quantitative. Protons and neutrons each fill their own parallel set of quantum energy levels, like two ladders standing side by side. If the proton ladder and the neutron ladder are roughly the same height, the nucleus sits in a low-energy configuration and stays stable. load the neutron ladder far higher than the proton ladder, and the extra neutrons are forced onto higher and higher rungs. Higher rungs mean more energy. More energy means a less stable nucleus. This penalty is embedded in the mathematics of nuclear structure. It is called the asymmetry energy, and it grows with the square of the imbalance between neutron count and proton count. Double the imbalance, and the cost goes up fourfold. Triple it, and the cost rises ninefold. The penalty is steep. In practical terms, this is a strict constraint on how many neutrons any nucleus can tolerate. For oxygen, which has 8 protons, the stable forms allow only 8 or 10 neutrons alongside those protons. Add enough extra neutrons, and the nucleus becomes radioactive, decaying in milliseconds. Add more still, and the nucleus does not exist at all. Heavy elements have more room. Lead with its 82 protons can sustain as many as 126 neutrons, which is still only about 50% more neutrons than protons. The imbalance has a ceiling everywhere. The ceiling is not smooth, though. It jumps in steps. Because certain numbers of protons or neutrons create especially stable configurations, much like the closed electron shells in an atom. These magic numbers push the boundaries slightly in ways that simple models cannot fully predict. Beyond the last stable configuration for each element, the nucleus hits its wall. Add one more neutron, and it falls out immediately. That wall has a name, and finding it in the laboratory has required some of the most powerful machines humans have ever built. But before we map that wall, we need to understand the quantum rule behind it properly, because that same rule will return in a far more dramatic form when we watch it try to stop the gravity of a dead star. Wolfgang Pauli was 25 years old when he wrote down the rule that would eventually slow gravity itself. He was thinking about electrons in atoms, trying to explain why electrons do not all collapse into the lowest energy state. The lowest rung on the energy ladder should fill first, and then all the electrons should stop there. Instead, they spread out across every available level, 2 electrons per rung, filling the ladder from the bottom up in an orderly staircase. Pauli proposed the reason. Each electron occupies a unique quantum state defined by a set of quantum numbers describing its energy, orbital shape, orientation, and spin. No 2 electrons in the same atom can share the same full set of those numbers. This rule applies to every fermion. Electrons, protons, neutrons, quarks, all of them obey it absolutely. Wherever you try to stack identical fermions, the exclusion principle pushes back. There is no threshold below which the rule relaxes. The reason the pushback grows with compression comes from the Heisenberg uncertainty principle. Confine any particle to a smaller volume, and its momentum becomes less certain, which means it must carry higher average momentum. Higher momentum means higher kinetic energy. Pack fermions tighter, and they are forced into higher energy states that push outward against whatever is confining them. This quantum pressure is unlike anything from ordinary physics. It has nothing to do with temperature. Even at absolute zero, even in the coldest possible object, a dense collection of fermions generates this outward pressure. It is purely mathematical, purely quantum mechanical, completely unavoidable. In atoms, this pressure keeps electrons in their shells. In white dwarf stars, it keeps the electron gas from compressing further under gravity. In neutron stars, as we will see, it is the force attempting to hold up an object more massive than the star that holds our planet in its orbit. But the exclusion principle is not infinitely powerful. Under certain conditions, it weakens, it flattens. Exactly how it flattens, and when, is what determines the maximum number of neutrons that can be stacked before everything fails. Before we get to that breaking point, we need a map. Physicists built one over decades, charting every known combination of protons and neutrons, and when you see it, the shape of nuclear stability becomes unmistakable. Draw a grid. Put the proton count along one axis, the neutron count along the other. Every point on that grid represents a possible nucleus. A small fraction of those points are stable. Most are radioactive. Many simply cannot exist. Scientists call this the chart of nuclides, and it is one of the most information-dense pictures in all of science. Around 3,000 points on that chart have been confirmed through experiment. Theory suggests the total number of nuclei that can exist, however briefly, stretches somewhere between 7,000 and 10,000 points. Everything beyond those limits is forbidden. You cannot make those nuclei even in the most powerful accelerator ever built. The stable nuclei cluster in a narrow band running diagonally from the lower left corner of the chart toward the upper right. For light elements, the stable zone sits right along the diagonal where proton count equals neutron count. Stray too far in either direction and you enter radioactive territory. Stray far enough and you reach the drip lines. The proton-rich boundary of the chart, the proton drip line, is mapped all the way to the heaviest elements researchers have ever synthesized. Beyond the proton drip line, nuclei shed protons spontaneously. That side of the map is known. The neutron-rich side is a different story entirely. Moving toward more neutrons, the nuclei become progressively more unstable. Their half-lives drop from billions of years to millions to hours to seconds to milliseconds. At the far edge, isotopes live long enough to be created in a particle beam and detected once before vanishing. Beyond those, nothing. The neutron drip line is the edge of everything on the neutron-rich side. It marks the exact point where the next neutron cannot bind, where it falls immediately out of the nucleus in less time than light takes to cross a proton. A nucleus sitting at the drip line holds its neutrons. The nucleus, one step beyond, sheds the extra neutron instantly. Here is the remarkable thing. The neutron drip line has only been directly confirmed by experiment up to element 10, which is neon. For every element heavier than neon, the location of the drip line is a theoretical estimate, tested in only a handful of cases by the most advanced radioactive beam facilities operating today. Thousands of isotopes that must exist between what has been confirmed and the actual drip line have never been seen, never been measured, never been created in a laboratory. The map is less than half complete. Reaching the drip line requires smashing nuclei at extreme speeds, sifting through the debris in microseconds, and identifying fragments that decay before any ordinary detector would have time to register them. The machines doing this job are operating right now, and what they find at the edge of the chart matters enormously for the rest of this story. 8 protons, the 8th element on the periodic table, the oxygen you breathe. The stable forms carry 8, 9, or 10 neutrons alongside those 8 protons. Extend the count to 16 total neutrons in an oxygen nucleus, and the half-life drops to microseconds. Push further, and the nucleus exists for such a tiny fraction of a second that only purpose-built detectors can confirm it was ever there. Push to 18 neutrons in an oxygen nucleus, and the drip line. The nucleus cannot hold that extra neutron, even for the time it takes light to cross a single atom. Now, add 3 protons. You are at sodium, the 11th element. And here the chart does something that catches most people off guard. The maximum neutron count for sodium jumps by 12, from 16 in oxygen to 28 in sodium. 3 extra protons unlocked 12 additional neutron slots. The reason is nuclear geometry. Oxygen, at its neutron drip line, sits at a perfectly closed nuclear shell, a round, compact, spherically symmetric arrangement. Adding protons to reach sodium pushes the nucleus into a deformed shape, elongated like a rugby ball, and that deformation opens entirely new energy levels. More levels mean more room for neutrons. This non-uniformity runs throughout the chart. Every time you add protons and cross one of the preferred quantum configurations, the neutron capacity jumps in ways that require detailed quantum mechanical calculations to predict. Those calculations are still being tested against experiment, element by element. For the heaviest elements, the maximum neutron count grows substantially. Lead can carry 44 more neutrons than protons. Uranium carries even more. The ratio still has a ceiling though. Even in the heaviest stable nuclei, the neutron excess is bounded by the asymmetry energy enforcing its penalty. The machines doing this work are rare isotope beam facilities. They accelerate stable nuclei to significant fractions of the speed of light, crash them into targets, and sort the debris by mass and charge in the microseconds before each fragment decays. What they find at the edge of the chart rewrites the textbooks. One of those facilities recently found something that expanded the sodium drip line dramatically. Another is just getting started and promises to double the number of known isotopes within a decade. The frontier is moving fast, and where the drip line actually falls matters enormously for something that dwarfs all of nuclear physics in scale. To understand why, we need to follow the neutrons all the way to the edge of the chart. Laboratories that hunt for the neutron drip line look nothing like what most people picture when they imagine physics research. There are no beakers. There are no microscopes. There are kilometer-long accelerator tunnels, room-sized detector arrays cooled toward absolute zero, and computers sorting millions of events per second looking for one nucleus among thousands that existed for a fraction of a second before vanishing. The radioactive isotope beam factory in Japan pushed the known neutron drip line to neon in 2022. Researchers there fired beams of stable nuclei at a beryllium target at enormous energies and let the resulting fragments shower through a series of magnetic separators designed to pick out specific mass-to-charge ratios. Each separator acts as a filter, letting one type of nucleus pass while deflecting everything else. At the end of the chain, a detector confirms the identity of what arrived. Neon with 24 neutrons. Confirmed. Drip line reached. The same facility confirmed that sodium with 28 neutrons exists at or beyond the sodium drip line. In those experiments, the sodium nucleus was detected one atom at a time. Its identity confirmed by the decay products it emitted in the first few microseconds after creation. Across the ocean, the facility for rare isotope beams in Michigan began operating in 2022 as well. Its early experiments confirmed isotopes near the sodium drip line independently. This machine will eventually push the experimental frontier dramatically further because it produces exotic isotopes at rates orders of magnitude higher than any previous facility. More beam means more rare events, which means more drip line mapped. Why does this matter beyond the immediate scientific interest? Because the drip line is the highway that the universe uses to build gold. The process that forges heavy elements, the rapid neutron capture process, sends nuclei crashing along the boundary of the neutron drip line. In environments so dense with free neutrons that even a fraction of a second of decay is too slow to compete, ordinary nuclei capture neutrons faster than those neutrons can decay. The nuclei race up the neutron-rich side of the chart, accumulate neutrons all the way to the drip line and sometimes beyond, and then beta decay their way back towards stability. Each step forges a heavier element: strontium, barium, gold, platinum, uranium. The exact path those nuclei take depends on exactly where the drip line falls. If the drip line for a given element sits at a different neutron number than theory predicted, the path changes, the forging rates change, and the final mixture of elements that spills out of the explosion changes. Every measurement at one of these facilities rewrites, in some small way, the recipe for the gold in your ring. And those measurements point toward a conclusion that has been building since the opening of this video. The drip line is the absolute ceiling for nuclear stacking. Beyond it, no force inside the nucleus can hold another neutron. The story of neutrons inside atoms ends at the drip line. The story of stacking neutrons has barely begun. All the gold that has ever existed, every gram in every vault, and every ring and every circuit board on this planet was forged in a moment of impossible density. The drip line is the route map for the process that built half the periodic table. The rapid neutron capture process threads directly along the neutron drip line, running through the most neutron-rich nuclei that physics allows, forging elements heavier than any stellar furnace can produce on its own. Here is how the forging works. In an environment dense enough with free neutrons that a fraction of a second is too long to wait for decay, nuclei can capture neutron after neutron before the previous capture has a chance to decay. The nucleus is pushed steadily up the neutron-rich side of the chart, accumulating mass without gaining protons. It gets forced toward and sometimes past the drip line. Then the nucleus hits a configuration it cannot hold, and it beta decays. A neutron flips to a proton, and the nucleus steps one element higher on the periodic table. A heavier element now stands where the lighter one was, with a fresh appetite for neutrons. The process repeats, building through strontium, then barium, then the heavy lanthanides, then gold, then platinum, then uranium. The abundances of all these elements in the universe, the ratio of gold to platinum to europium to lead, encode the exact path the rapid neutron capture process took through the drip line. Change the drip line's location, change the nuclei it runs through, and you change those ratios. Every experiment at a rare isotope facility carries implications for nuclear physics, for chemistry, for astronomy, and ultimately for the question of why your planet has the composition it does. For decades, astrophysicists debated where the rapid neutron capture process actually happens. Supernova explosions were the leading candidate. The conditions inside a collapsing stellar core are violent, yes, but the neutron densities in the outer layers where ejector escapes may not be extreme enough to drive the full chain from iron all the way to uranium. The answer, when it finally arrived, came in a signal that traveled as a ripple in spacetime rather than as light. In 2017, two objects collided 130 million light-years from Earth. The ripple in spacetime arrived at detectors in the United States and Italy, and for the first time, the source of the universe's gold was confirmed beyond any reasonable scientific doubt. To understand why that collision worked, why it produced exactly the conditions the drip line demands, requires understanding the objects that collided. And those objects are so extreme that a nucleus sitting at the neutron drip line would look ordinary by comparison. After everything we have covered, the ceiling for nuclear stacking begins to come into focus, and the picture is both precise and deeply incomplete. For any given element, the neutron drip line defines the maximum. Add one neutron too many, and it falls out immediately. The nucleus refuses to hold it. This is the absolute boundary that the strong nuclear force, combined with quantum structure, imposes on how many neutrons can live inside an atom. For calcium, with 20 protons, the most sophisticated nuclear models predict the drip line sits around 51 neutrons. That is more than double the proton count. 51 neutrons packed alongside 20 protons, held together by a force that operates only at the shortest distances, constrained by energy levels that must remain within the rules of quantum mechanics. Beyond that number, no calcium nucleus can exist. Even in the most powerful accelerator ever built, the total number of nuclei that physics allows across all elements is estimated somewhere between 7,000 and 10,000. Humans have directly observed only about 3,000 of them. Thousands of isotopes that theory predicts exist remain unmeasured, unseen, unconfirmed. The map is less than half complete, and the work of completing it will occupy physicists for generations. What is remarkable about the drip line is that it genuinely is the limit of what nuclear structure can do. The strong nuclear force is the most powerful of the four fundamental forces at short range, stronger than electromagnetism by orders of magnitude, incomparably stronger than gravity at the distances between quarks. Yet even the strong force runs out of capacity. Even the most powerful force in the universe at close range hits a wall. What could possibly do better? Gravity operates by an entirely different set of rules. It pulls at everything with mass, indifferently, without paying any of the energy penalties that govern nuclear structure. The asymmetry tax is irrelevant to gravity. The ladder of quantum energy levels is equally invisible to it. The strong force can hold a few hundred neutrons together in the densest nucleus. Gravity has held together objects containing a number of neutrons so vast that writing it as a word would fill a paragraph. The strong force is the strongest force at short range. Yet, it cannot compete with what gravity does over cosmic scales and cosmic timescales. The drip line is the ceiling for nuclear stacking. Gravity can stack neutrons in a way that makes the drip line look like a counting exercise for children. To see what gravity can do, we need to watch a star die. Every massive star lives by a careful bargain. Gravity pulls every gram of the star's material inward without pause or preference. Nuclear fusion pushes outward with equal persistence. For millions of years, sometimes billions, these two forces hold each other precisely in check, and the star burns steadily, reliably, generously. Then the fuel runs out, and what follows is among the most violent sequences of events the universe knows how to produce. It does not happen all at once. Stars burn through a sequence of fuels in order of increasing difficulty. Hydrogen fuses into helium across millions of years. When hydrogen in the core is exhausted, helium ignites and burns for a few 100,000. Then carbon follows, then oxygen, then neon, then silicon, each stage burning hotter and faster than the last, each producing a heavier product that immediately becomes the fuel for the next round. By the time a massive star is burning silicon, the schedule has become desperate. Hydrogen burning lasted 10 million years. Silicon burning lasts 1 day. The star is racing through its remaining nuclear fuel at accelerating speed, reaching higher and higher temperatures to extract ever smaller returns from what is left. The layers of the star at this stage look like a cross-section through a chemistry set, gone catastrophically wrong. Each element fusing in a separate shell, each shell feeding into the next. Silicon burning produces iron, and iron is where the star's internal logic collapses. Every element lighter than iron releases energy when fused. Hydrogen, helium, carbon, oxygen, all the way up. Each fusion reaction pays out. Iron sits at the floor of the nuclear energy landscape. Fusing iron absorbs energy rather than releasing it. The furnace goes cold the moment it tries to burn its own ash. The iron core at this point has accumulated a mass comparable to the object that holds our planet in orbit. Dense, hot, and supported entirely by the pressure of its electron gas, because the nuclear fire that created it has already died. The electrons push out. Gravity pulls in. For a brief moment, precarious equilibrium holds. But the silicon shell above the core keeps burning, raining more iron down. The core grows heavier. At a critical mass, electron pressure cannot hold the weight. The outer layers of the star still have no idea. Light from the deep interior has been traveling outward for so long that when the core gives way, the surface does not register anything for hours. From outside, the star looks unchanged. In the core, something that takes less than 1 second has already begun. The iron core falls inward at a significant fraction of the speed of light. An object containing more mass than the one holding this planet in its orbit collapses from a sphere hundreds of miles across to a sphere smaller than most cities in less than a heartbeat. And what the crushing forces the matter to do in that fraction of a second sounds, on first hearing, physically impossible. As the iron core collapses, the pressure on its electrons grows beyond anything achievable in any laboratory on Earth. Electrons are forced into smaller and smaller volumes, The Heisenberg uncertainty principle demands they carry higher and higher momenta. At a critical threshold, the electrons become so energetic that they are pushed directly into the protons around them. An electron and a proton collide and merge. A neutron emerges. A neutrino streaks away at nearly the speed of light. This is inverse beta decay. The decay process familiar from the early chapters of this story reversed under compulsion. In ordinary conditions, a neutron decays into a proton by releasing an electron. Here, with the electrons forced to carry enormous energy, the reaction runs backward. Protons absorb electrons and become neutrons. The entire core is converting, particle by particle, from iron nuclei into a vast, dense mass of neutrons. The neutrino output is staggering. In a few seconds, the collapsing core releases more energy in neutrinos than the star that holds our planet in orbit will radiate in its entire lifetime as visible light. For a fraction of a second, measured in neutrinos, the collapsing stellar core is the most luminous object in the observable universe. In 1987, a massive star in a satellite galaxy, roughly 160,000 light-years from Earth, collapsed and exploded. 17 seconds before the optical flash reached any telescope, detectors buried in mines on 3 continents simultaneously registered a burst of neutrinos. 24 of them, in 17 seconds, each carrying energy that dwarfed any particle beam ever made on Earth. Those 24 particles were a tiny fraction of the roughly 10 to the 58th neutrinos produced in the collapse. They traveled 160,000 light-years and still triggered detectors here, which tells you something about the total output. That event was the first and still only direct detection of a supernova neutrino burst, and it confirmed that the picture of inverse beta decay driving the collapse was correct. The collapse continues. The density climbs. And then the core hits something that stops it cold. At a certain density, the separation between neutrons shrinks below the distance at which the nuclear force flips from attractive to repulsive. The nuclear hard core activates. Matter becomes nearly incompressible at this threshold, stiff as nothing else in existence. The entire collapsing core, which has been falling for less than a second, abruptly reverses. The bounce sends a shockwave outward through the infalling material. The shockwave stalls. Neutrinos pouring from the core pump energy back into the stalled front. The shock revives. It tears outward through the outer layers, and in seconds the star blows itself apart. Everything that was the stellar exterior, every layer forged across millions of years of burning hydrogen, helium, carbon, oxygen, all of it flung outward into space at thousands of miles per second. What the shockwave leaves behind is what this entire story has been building toward. A sphere of neutron matter, smaller than most cities, more massive than the object that keeps our world in orbit, formed in milliseconds from what was a stellar core seconds before. A neutron star. And yet, calling it a star undersells the situation entirely. Its surface alone is stranger than any material a terrestrial laboratory has ever created. Descend through the layers, and the strangeness increases with every mile. Born in less time than it takes to blink from the ruins of a collapsing core, the neutron star immediately presents numbers that resist ordinary comprehension. Roughly 2 of the masses that hold planets in orbits like ours, compressed into a sphere 12 to 13 miles across. The density at the center climbs to conditions found nowhere else in the observable universe. A teaspoon of material from that center would weigh more than every building, vehicle, road, and living creature on Earth combined. More than all of it. 5 billion tons balanced on a kitchen spoon. The surface gravity is 100 billion times stronger than the gravity keeping you grounded right now. The escape velocity at the surface reaches between 30 and 50% of the speed of light. To escape a neutron star, you must move fast enough to cover the distance from Earth to the Moon in less than 2 seconds. The magnetic field of a newborn neutron star can be trillions of times stronger than the most powerful electromagnet ever built in a laboratory. Strong enough to pull iron from hemoglobin in your blood if it were anywhere within several 100,000 miles of you. All of this from an object smaller than Los Angeles. The newborn neutron star is also spinning. Conservation of angular momentum, the same principle that makes a spinning figure skater speed up when they pull their arms inward, takes the slow rotation of the massive stellar core and amplifies it enormously as the material collapses to a fraction of its original size. A star that rotated once every few weeks before the collapse can become a neutron star spinning dozens or hundreds of times every second. Some of the fastest known neutron stars complete over 700 rotations per second, their entire surface moving at a significant fraction of the speed of light. The newborn star is also blazing hot, radiating in X-rays. Fresh from the collapse, its surface temperature can reach 1,000,000 degrees or more, hot enough that the thermal radiation peaks far into the ultraviolet and X-ray spectrum, invisible to the human eye but visible to space telescopes. Over thousands of years, the star cools. The heat slowly leaks out through the layers of dense matter, constrained by the extraordinary thermal conductivity of the crust. And eventually, the star fades from X-ray brightness to a dimmer, quieter object. But the spin remains, and the magnetic field remains, and together they produce something remarkable. A spinning magnetic neutron star sweeps its magnetic poles across space like a lighthouse. Charged particles, accelerated near the poles, emit radiation, and that radiation forms a beam. If the beam sweeps across Earth, we detect a pulse. A radio pulse arriving with the regularity of an atomic clock, hundreds of times per second, from an object 12 miles across 20,000 light-years away. A pulsar. And the star is made, overwhelmingly, of the particle we met in the earliest chapters. The inverse beta decay process that ran backward during the collapse converted most of the stellar core's protons into neutrons. A small fraction of protons, electrons, and heavier charged particles remain, but the dominant constituent by far is the neutron. The drip line, that hard boundary in a laboratory where a nucleus can no longer hold its neutrons, is now completely irrelevant. Gravity has stacked neutrons in quantities that exceed the drip line limit by 56 orders of magnitude. But the star is layered, and each layer is stranger than the one above it. The surface is where the story of these neutrons continues, and even there, on the outermost shell of this extraordinary object, the matter is already far beyond anything terrestrial physics can produce or directly study. Peeling back the outer surface of a neutron star reveals a crust, a rigid shell roughly 1 mile thick, covering the neutron interior like the rind on a fruit made of extremes. This crust is a crystal, a vast, structured lattice of atomic nuclei arranged in orderly rows, embedded in a dense sea of relativistic electrons. The nuclei here are deeply neutron-rich, pushed far past any isotope a rare isotope beam facility has ever created, held in this configuration by the collective pressure of the entire star rather than by nuclear binding alone. They do not exist in any periodic table. They have no names in chemistry. They are matter in a configuration that has no terrestrial analog. The outermost layer of the crust behaves somewhat like a metal. Electrons flow through the nuclear lattice, conducting heat and electricity. There is a distant, distorted resemblance to ordinary crystalline solids. Descend a few hundred yards and that resemblance begins to fade. The nuclei grow more and more neutron-rich as the pressure increases with depth. Each additional yard down pushes the nuclear composition further into territory that no experiment has directly probed. The extreme gravity shaping this crystal has one spectacular consequence. A mountain on a neutron star crust, a bump, a ridge, any deviation from a perfect sphere cannot be taller than a few inches. The surface gravity is so intense that any protrusion above a few centimeters would be crushed flat by its own weight. The crust is the smoothest object in the observable universe, proportionally smoother than any billiard ball ever polished. And yet, even those sub-centimeter bumps matter. If a neutron star is spinning hundreds of times per second with even a microscopic asymmetry in its crust, the rotating mass wobbles slightly. And that wobble emits gravitational waves. The smoother the crust, the quieter the signal. The rougher the crust, the louder. Gravitational wave observatories searching for these continuous waves from spinning neutron stars are, in effect, measuring the surface roughness of objects 12 miles across and thousands of light-years away. When the crust occasionally fractures under the magnetic stresses that build as the star spins down, the energy release can be enormous. The starquake produces a burst of X-rays and gamma rays detectable across the galaxy. Instruments on Earth have recorded these events from neutron stars tens of thousands of light-years distant, carrying energy in milliseconds that would take the entire power output of our star years to equal. At a particular depth, the density crosses a critical threshold. The nuclei have accumulated so many neutrons that their binding energy can no longer contain all of them. Neutrons begin to drip free. Here the word earns its meaning at the most literal level. Free neutrons genuinely leak out of the nuclei and fill the space between them, creating a superfluid that percolates through the crystalline matrix like water through gravel. This is the neutron drip point inside the actual star, and it marks the transition into the inner crust. Below it, free neutrons flow in a quantum superfluid between the nuclear clusters. The crystal becomes something stranger, part solid lattice and part flowing quantum fluid simultaneously. The mechanical properties shift dramatically at this boundary. Above the drip point, the crust is rigid. Below it, the superfluid neutrons change everything about how the material responds to stress, twisting, and the subtle torques of a spinning star. But the inner crust has something even more remarkable waiting deeper in, because as the density climbs further, the nuclear clusters stop being spherical. They start to deform, and the shapes they take are named after food, because the physicists who first calculated them needed an analogy that people could actually picture. Deeper in the crust of the neutron star, spherical nuclei stop being the lowest energy option. The competition between nuclear attraction, which pulls matter together over short distances, and the electromagnetic repulsion of the protons still present in the mix, which tries to push the positively charged material apart, finds a new balance at higher densities. That balance produces shapes that belong in a kitchen, not a physics textbook. The spherical clusters elongate first. Instead of round blobs of nuclear matter floating in a superfluid of free neutrons, the clusters stretch into cylinders. Long, parallel rods of nuclear matter threading through the neutron background, dense enough to make the outer crust look airy. Physicists call this phase nuclear spaghetti, and the name earns its place. The rods extend through the material in arrays, each one a cylinder of matter at densities exceeding anything in any atomic nucleus ever created in a laboratory. Add more density, and the rods flatten into sheets. Planar layers of nuclear matter alternating with sheets of free neutrons, extending in every direction, stacked like geological strata made of something a billion times denser than rock. Nuclear lasagna. The geometry is exactly what the name describes. Infinite, flat slabs of nuclear matter, separated by thin gaps of free neutrons, repeating without a natural boundary. Increase the density further, and the geometry inverts. Above the inversion, nuclear matter is the minority, forming clusters inside a majority background of free neutrons. Below the inversion, the roles reverse. Nuclear matter becomes the background, and now cylindrical tunnels of free neutrons run through it. The inverse of spaghetti. Then the geometry completes its full reversal, becoming spherical bubbles of free neutrons embedded inside nuclear matter, the inverse of the original clusters. Here is the property that makes this more than a naming exercise. Nuclear pasta is calculated to be the strongest material in the observable universe, by a factor of billions compared to the strongest steel. A mountain of it would be essentially impossible to deform under any force available in any terrestrial setting. When a neutron star spins, any asymmetry in its pasta layer continuously radiates gravitational waves into space. Gravitational wave observatories are already searching for this signal because the strength of what they find, or fail to find, constrains the breaking strain of the pasta holding the crust together. Below the pasta layer, the organized structures dissolve entirely. The inner crust ends, and what begins is a region better understood in some ways, and more alien in others, than anything above it. Crossing from the inner crust into the outer core of the neutron star, the organized structures vanish and matter becomes uniform. No nuclei, no clusters, no sheets, no pasta. Instead, a continuous fluid, roughly 95% neutrons, a small fraction of protons, and enough electrons and heavier cousins of electrons, called muons, to keep the electric charge balanced throughout the volume. This is the outer core, and it occupies most of the star's interior. A typical neutron star is 12 to 13 miles across. The crust takes up the outermost mile. The inner core, the mystery zone, claims the innermost few miles. Everything between is outer core, a vast region of dense nuclear fluid. Nuclear theory reaches here, extended with moderate confidence from laboratory measurements. The equation of state, the relationship between pressure and density that determines how the material responds to compression, can be calculated for the outer core with uncertainties that are large but at least bounded. This is the best understood part of the star's interior. And that context matters. Even the best understood region contains matter packed more tightly than any nucleus ever made in a laboratory, with pressures so extreme that no human instrument has come close to directly measuring anything like them. The nucleons here, neutrons and protons, are deformed by proximity. Each one is within touching distance of its neighbors, constantly exchanging the force-carrying particles of the strong interaction, unable to be assigned a clean individual identity the way a single nucleus in a laboratory can be. The outer core is a quantum many-body system of extraordinary complexity, and the equations describing it are some of the most computationally demanding in all of physics. The outer core also harbors something else. Theory predicts that in this region, the neutrons form a superfluid. The same pairing mechanism that creates superconductors in metals allows neutrons to pair and condense into a collective quantum state. The small fraction of protons present likely forms its own superconducting phase. These quantum states affect how quickly the star cools, how it responds to being spun up or spun down, and how it recovers from events like the occasional pulsar glitch that shakes its structure. The cooling history of neutron stars is, in fact, one of the few windows into the outer core. A newly born neutron star cools rapidly through neutrino emission in its first 1,000 years or so, then more slowly through photon emission from its surface. The rate of cooling, measured in X-rays by space telescopes, encodes information about the pairing states of the neutrons and protons inside, because paired neutrons emit neutrinos through different channels than unpaired ones. The cooling curves of several neutron stars have already provided evidence for neutron superfluidity in the outer core, making the outer core the one region of the neutron star interior where we have at least some indirect observational access to the quantum state of matter. Go deeper, past roughly twice the density found at the center of an ordinary atomic nucleus, and the reliable theory stops. The nuclear equations of state that work in the outer core lose their validity. The quark-level theory of the strong force, which works at very high densities, does not yet work at intermediate densities. There is a gap, a window of density where no framework currently in existence provides a reliable calculation of what the matter does. What fills that window is one of the largest open questions in physics. 4 competing possibilities dominate the debate, and each one changes the star's behavior in ways that, in principle, can be observed from tens of thousands of light-years away. Reaching the inner core means entering the most inaccessible volume in the observable universe. Nothing leaves it. No photons, no neutrinos after the first few seconds of the star's birth, no particles of any kind. The only information that escapes from the inner core is encoded indirectly in the star's mass, its radius, how it vibrates, and how it deforms under the gravity of a companion. The first candidate for the inner core is hyperons. At densities above twice nuclear saturation, neutrons can convert into heavier relatives that carry strange quarks. Lambda, sigma, and Xi particles, all well measured in laboratory accelerators, would appear spontaneously once the density creates enough energy to sustain them. Their appearance seems physically reasonable. They are known particles. The problem is the maximum mass. Hyperons soften the equation of state. Their appearance opens new energy channels, spreading the quantum mechanical energy over more degrees of freedom, which lowers the pressure at a given density. Lower pressure means less resistance to gravity. Less resistance means a lower maximum mass for the star. Yet, neutron stars have been measured above twice the mass of the object keeping our planet in orbit. A hyperon-filled core struggles to explain those masses. This contradiction is the hyperon puzzle, and it has no fully accepted resolution. The second candidate is a kaon condensate. Kaons carry strange antiquarks and normally decay rapidly in vacuum. At high densities, the quantum field of kaons can settle into a coherent collective state. This condensate would also soften the core, creating the same tension with observed high-mass stars. The third candidate is quark matter. At very high densities, the boundaries of individual neutrons and protons dissolve. The quarks inside them stop being confined within individual particles and begin moving through the entire core volume. This deconfinement could be a sharp phase transition or a gradual crossover. And either way, it changes the equation of state dramatically. Here is what elevates this from pure speculation. Statistical analyses combining gravitational wave data, X-ray timing measurements, and radio pulsar masses suggest that the most massive neutron stars probably contain quark matter at their centers. The data does not yet confirm this definitively. The data increasingly points there. There is a fourth possibility, and it is the most radical of all. In the mid-1980s, a theorist proposed that strange quark matter, containing roughly equal portions of up, down, and strange quarks, might be the lowest energy state that matter can occupy. Lower energy than iron, lower than any ordinary atomic nucleus. If this is true, any large collection of ordinary nuclear matter sitting at room temperature would be in a permanent state of slow decay towards strange quark matter, held back only by the enormous energy barrier of quantum tunneling. In that scenario, neutron stars would be strange quark stars, their entire volumes converted to a quark phase far more exotic than deconfined neutrons and protons. We would have no way to tell the difference from the outside. This idea, the Witten hypothesis, remains theoretically open. Some parameter combinations allow it, others forbid it. The observations needed to test it are nearly identical to the observations needed to distinguish ordinary neutron matter from quark matter, very precise mass-radius measurements for many stars. What that quark matter might actually be doing at those densities is where the story takes its strangest turn yet. Quark matter at high density does not simply sit inert. It pairs. In ordinary metallic superconductors at very low temperatures, electrons form coupled pairs through a slight interaction with the surrounding atomic lattice. Two electrons with opposite momenta bind into what are called Cooper pairs. those pairs condense together into a single collective quantum state, and the material loses all electrical resistance. Superconductivity emerges. At the densities found in the innermost core of a neutron star, quarks do the same thing. The strong nuclear force contains attractive channels between pairs of quarks with opposite momenta, and at sufficient density, those channels drive the quarks into pairs. The result is a color superconductor. The name comes from the color charge that quarks carry, the quantum chromodynamic equivalent of electrical charge. At the highest theorized densities, the pairing reaches a phase called color flavor locking. All three flavors of quarks present at those densities, up, down, and strange, pair together in a pattern where color and flavor interlock. The color flavor locked phase is electrically neutral by itself, without requiring free electrons to balance any charge. It is simultaneously a superfluid and a superconductor. It has no equivalent in any terrestrial material. Consider for a moment what this means for the star's interior. Superfluidity means matter flows without resistance, with no friction, no energy loss from circulation. If a superfluid forms a vortex, that vortex persists indefinitely. Superfluid neutrons in the outer core have been circulating in the same vortex pattern since the star formed, carrying angular momentum that the crust must periodically catch up with. When the crust suddenly catches up, the star's rotation rate briefly accelerates in what observers detect as a pulsar glitch, a sudden jump in spin frequency. The glitches happen. The superfluid vortices driving them are, according to theory, right there in the neutron star's core and crust, flowing in patterns governed by quantum mechanics at stellar scale. The color superconducting state in the inner core, if it exists, would be stranger still. Quarks paired across all three flavors. The strong force mediating an exotic molecular bond at densities far beyond nuclear matter. The interior of the star locked into a single coherent quantum phase stretching miles across. In 2024, researchers performed a statistical analysis combining data from gravitational wave observatories, X-ray space telescopes, and radio pulsar timing to extract the first observational constraint on the pairing strength of this exotic state. They cannot look directly inside the star, but the mass, the radius, the tidal response of the star during a merger, all of these encode information about the pressure deep in the core, and pressure carries a fingerprint of the quantum pairing. The pairing strength has been bounded from the outside by observers tens of thousands of light years away. All of this inner chemistry matters deeply, but there is a question that supersedes it. Whatever the inner core contains, the star exists only because something is holding it up against the gravity trying to crush it. That something is a force unlike any discussed so far, a pressure generated by nothing except the mathematics of quantum mechanics itself. Pack enough neutrons into a small enough sphere, and a purely quantum pressure builds. Its source is a single fact. Neutrons are fermions, and fermions refuse to share quantum states. Cool the star to absolute zero, and the pressure remains at full strength. Strip away nuclear forces and the pressure remains. The only thing that matters is the fermion nature of the neutrons themselves. The Pauli exclusion principle, which kept electrons in atomic shells and blocked neutron decay inside nuclei in earlier chapters of this story, now operates at the scale of a star. Every neutron must occupy a unique quantum state. Every low-energy state is already claimed. The last neutrons added are forced into the highest available momentum states, because there is nowhere else to go. Those high-momentum neutrons push outward. They carry kinetic energy, and kinetic energy creates pressure. This pressure does not diminish as the star cools. Cooling a normal gas reduces its pressure because temperature drives the kinetic energy of its particles. Neutron degeneracy pressure is immune to temperature. Remove every last unit of heat from a neutron star, and the pressure persists at full strength, because the pressure does not come from thermal motion. It comes from the quantum prohibition against two identical fermions sharing a state. The total kinetic energy stored in this degenerate neutron sea inside a typical neutron star is comparable to the total gravitational binding energy of the star, the energy you would need to supply to lift every neutron completely out of the gravitational well. These two energies are locked in a rough balance. The quantum wall is strong enough to match gravity, and the star exists. Here is one way to feel the scale of that. Every neutron in the star is moving fast. The typical neutron near the center is carrying a momentum that would correspond to kinetic energies far above what particle accelerators on Earth routinely produce for nuclear experiments. And it is moving that fast, carrying that energy, purely because the Pauli exclusion principle has nowhere lower for it to sit. The star is a body of extreme quantum agitation, even without any heat driving it. Even if you could somehow cool a neutron star to absolute zero, it would look and behave almost identically, because the pressure driving everything is not thermal. A white dwarf runs on the same principle, using electrons instead of neutrons. Because electrons are nearly 2,000 times lighter than neutrons, they become relativistic at much lower densities, and the maximum mass a white dwarf can support tops out at roughly 1 4/10 of the mass of the object that holds our planet in orbit. Neutrons require far higher densities before their degeneracy pressure becomes significant, and they can support a far heavier star. The neutron version of the same wall is both more powerful and more resistant to the relativistic weakening that ultimately destroys it. The neutron degeneracy wall is formidable. It stands as one of the strongest pressure sources in the observable universe, and it has a weakness built directly into the laws of physics. Consider what happens inside the most massive neutron stars, where the outermost neutrons in the degenerate sea are moving at velocities approaching the speed of light. In a less compressed star, neutron degeneracy pressure grows with the fifth power of the neutron number density. Compress the neutrons by a small amount and the pressure rises steeply. The wall grows higher the more you press against it. This steep growth is what makes the degeneracy wall effective. When the neutrons at the top of the degenerate stack become relativistic, the exponent drops. Pressure now grows with density to the power of 4/3. The wall still increases with density, but more slowly. The steepness flattens. The resistance is real but diminished. This flattening exists even in Newtonian physics. But neutron stars live in general relativity, and general relativity adds a second problem that turns the flattening into something much more dangerous. In general relativity, every form of energy contributes to the gravitational field. Mass is energy. Kinetic energy is energy. And pressure, the force that the star is using to hold itself together, is also a form of energy. A star exerting enormous internal pressure has additional mass energy from that pressure, and that mass energy curves spacetime and strengthens gravity. The feedback is direct. The star attempts to support itself with higher pressure. The higher pressure adds to the gravity the star must overcome. Increasing pressure to fight gravity inadvertently increases gravity in return. Think about what that means practically. A star that is slightly too massive for its current pressure begins to contract. The contraction compresses the neutrons, which should raise the pressure. But the raised pressure also raises the gravity. In a low-mass regime, the pressure wins the race. In a high-mass regime, where the neutrons are already relativistic and the pressure wall is flattening, the gravity wins. The contraction continues. There is no stable stopping point. The floor has given way. In the range of masses where neutrons are non-relativistic, this feedback is manageable, and the star survives. As the mass increases, the neutrons become more relativistic. The pressure wall flattens, and the feedback loop tightens. At a critical mass, the feedback becomes unbreakable. No increase in pressure can outrun the gravity it creates. Could quark matter, or some undiscovered phase, provide pressure that degeneracy pressure alone cannot? In principle, yes. A sufficiently stiff equation of state at high densities can push the maximum mass higher, but it cannot eliminate the feedback. The relativistic pressure-gravity coupling is a feature of curved spacetime, and no matter what the material is made of, its pressure still contributes to its own weight. The exotic matter can delay the breaking point, and does. The Tolman-Oppenheimer-Volkoff limit for realistic nuclear matter lies well above Oppenheimer and Volkoff's original estimate precisely because the nuclear hardcore repulsion is stiff. But the limit exists regardless. Exotic matter and improved nuclear physics cannot escape this. The feedback is written into the structure of general relativity itself. Pressure contributes to gravity exactly, at every radius, enforced by the mathematics of curved spacetime. The maximum mass of a neutron star exists because spacetime enforces it. That maximum mass has an equation, published in 1939, and its number is what every neutron star observation in history has been converging on. Oppenheimer and Volkoff published their calculation the same year that the word fission first appeared in a physics paper. The neutron had been discovered less than a decade before. Neutron stars were theoretical objects. Speculation from Bardet and Zwicky. Following the supernova of 1934, no one had ever seen one. Whether they could exist was unresolved. Their equation governs the balance between pressure and gravity inside any spherically symmetric, non-rotating object in general relativity. It is the relativistic form of hydrostatic equilibrium, the condition that keeps a star from collapsing or exploding. Unlike the Newtonian version, which treats pressure as a pure force, the Tolman-Oppenheimer-Volkoff equation includes pressure as a source of gravity on both sides of the balance. The mathematics enforces the feedback loop described in the previous chapter at every radius inside the star. When Oppenheimer and Volkoff solved the equation using non-interacting neutrons, a gas of particles pushing back only through degeneracy pressure, they found a maximum mass, a number above which no stable solution to the equation exists. Their result came out to roughly 7/10 of the mass of the object holding our planet in orbit. That seems surprisingly small. The reason is that non-interacting neutrons are an idealization. Real neutrons at high density repel each other at short range through the nuclear hardcore. This repulsion stiffens the equation of state and raises the maximum mass considerably. Include realistic nuclear repulsion, and the maximum mass climbs to somewhere between 2 and 2.5 of those reference stellar masses. Depending on what the equation of state does at the highest densities, the exact ceiling depends on the inner core. A stiff equation of state, where pressure rises rapidly with density, allows a more massive star. A soft equation of state, where exotic matter has opened new energy channels and flattened the pressure response, gives a lower ceiling. The uncertainty in the inner core is precisely the uncertainty in the Tolman-Oppenheimer-Volkoff limit. Current theoretical models combined with observational data place the true maximum mass between 2 and 2.5 times the reference mass. That range is the result of the best measurements in existence applied to the best theories in existence, squeezed down from the wide uncertainty of a decade ago to a narrow corridor. Closing it further requires finding the heaviest neutron stars in the universe and studying them closely enough to distinguish the competing equations of state. Some of those stars are being measured right now, and the results are already eliminating entire categories of theoretical models. One observation at a time, measuring the mass of a neutron star presents a particular challenge. Because neutron stars are small, distant, and radiate no visible light from a surface that chemistry or geology could analyze, they are too compact to resolve spatially with any telescope. The only tool that works, the one that has delivered every precise neutron star mass we have, requires a partner. When a pulsar orbits a companion star, its radio pulses travel toward Earth through ordinary vacuum for most of their journey. During certain phases of the orbit, though, the pulses must pass close to the companion before continuing on. General relativity predicts that a massive object bends spacetime around itself, and a signal traveling through that curved region takes slightly longer to arrive than it would through empty flat space. The delay is called the Shapiro delay, after the physicist who calculated it in 1964. That delay is small, measured in microseconds. But pulsars are natural clocks of extraordinary precision. Their pulses arrive with a regularity that rivals atomic clocks, allowing physicists to detect timing differences far below the duration of a single human heartbeat. By measuring how arrival times shift as the pulsar moves around its orbit, and how those shifts depend on the orbital geometry, the masses of both the pulsar and its companion can be extracted with remarkable accuracy. The first measurement that shattered the theoretical ceiling of the time arrived in 2010. A team studying a pulsar in the constellation Aquila found an object spinning nearly 300 times per second, orbiting a white dwarf companion in a nearly edge-on plane that maximized the Shapiro delay signature. The mass they extracted came in at nearly 2 times the mass of the stellar reference object, 2 full stellar masses compressed into 12 miles. That single number ruled out dozens of theoretical equations of state overnight. Every model that predicted maximum masses below about 1 8/10 of the reference mass was eliminated. The measurement went beyond constraint entirely. It decapitated an entire branch of the theory. 3 years later, a second confirmation arrived from a pulsar in Taurus, orbiting a white dwarf close enough that the companion's gravity measurably altered the orbital decay. A second data point, from a completely independent system, measured through a different method, sitting in statistical agreement with the first. A third followed. A pulsar spinning more than 300 times per second in the constellation Monoceros, characterized through timing analysis and later confirmed by an X-ray telescope operating from the International Space Station, came in at just above 2 reference masses as well. Each of these measurements carried the same message. The inner core of a neutron star must support pressures large enough to hold up an object twice the reference mass against collapse. Any equation of state that softens too much at high density, whether through hyperons, kaon condensates, or soft quark matter, predicts a maximum mass below the 2 reference mass threshold. The observations have closed off those soft options one by one. The stiffness required is real. The universe has been giving the answer across 3 separate, independent measurements from 3 different systems over a span of more than a decade. But even among these record holders, one stands alone. A pulsar whose mass sits at the very edge of what the best theories can explain, reaching that edge through billions of years of patient consumption rather than the violence of birth. Spinning 700 times per second in the constellation Sextans, about 20,000 light-years away, a pulsar has been feeding. Black Widow pulsars earn their name by consuming their companions. A fast-spinning pulsar floods its companion with high-energy radiation, ablating the smaller star's material away, gram by gram, year by year. Over timescales longer than the current age of complex life on Earth, the pulsar accumulates the stolen mass onto its own surface, growing heavier with each passing billion years. The companion dwindles. What was once a star becomes a wisp, barely heavier than a large planet, still orbiting in a few hours, still glowing faintly from the radiation bombarding it, slowly being eaten down to nothing. What remains of the companion in this system amounts to a few % of a reference stellar mass. The pulsar has consumed nearly everything else. And the pulsar itself is extraordinary. Spinning 700 times per second, its equatorial surface travels at a fraction of the speed of light with each rotation. The spin alone tells you something was transferred. A neutron star is born spinning quickly, but not that quickly. Reaching 700 rotations per second requires billions of years of accretion, spinning the star up like a cosmic gyroscope, each gram of infalling material adding angular momentum to the already dense, rigid body. When a team at the Keck Observatory measured the optical light from the tattered companion in 2022, they combined the pulsar's orbital dynamics with the companion's spectral properties to derive a mass. The result came in at 2 35/100ths of the reference stellar mass, with an uncertainty that places it among the highest measured for any confirmed neutron star. The center of this object contains matter at a density no laboratory has ever approached. No theory has fully mapped, and no direct observation can reach. One of the researchers who published the discovery noted afterward that the core of this pulsar harbors the densest matter accessible to observation anywhere in the observable universe. That statement was not rhetorical. It was the most precise claim the data allowed. If the true Tolman-Oppenheimer-Volkoff limit sits at the low end of current theoretical estimates, this pulsar is already brushing against it or perhaps exceeding it slightly, held above collapse by its rapid rotation, providing centrifugal support that a non-spinning star of the same mass would not have. If the limit sits at the high end, the pulsar has room to spare. The measurement cannot distinguish between these possibilities alone. Mass is only one dimension of the question. To constrain the equation of state fully, you need both mass and the physical size of the star. Two different equations of state can predict the same maximum mass while producing stars of very different radii at lower masses. Only by measuring both quantities for the same population of stars can the internal physics be separated from the observational degeneracies. That is precisely what a small telescope orbiting above the atmosphere began doing in 2017, and its results have proven stranger than most models anticipated. Orbiting Earth on the International Space Station, a soft X-ray telescope called the Neutron star. Interior Composition Explorer works by watching neutron stars spin. The instrument watches in X-rays, the high-energy radiation emitted by hot regions on the neutron star surface. Many pulsars have patches of the surface heated to extreme temperatures by infalling particles or magnetic field effects, and those patches glow brightly in X-rays. As the star spins, the hot spots sweep into and out of the telescope's line of sight, producing a pulse profile that rises and falls with each rotation. Decoding that profile requires modeling an extraordinary amount of physics simultaneously. Hotspots are points on a curved surface. Photons leaving those spots travel through the star's own gravitational field before reaching the detector, and the strong gravity bends their paths. The exact way the pulse brightens, peaks, and fades depends on the mass, the radius, the location of the hotspots, and the geometry of the system. All of these variables leave their fingerprints on the same pulse. A long enough observation can separate them. What the instrument found has been striking. A pulsar of about 1 1/3 reference masses has a radius close to 12.5 miles across. A pulsar of about 2 1/10 reference masses, considerably heavier, has essentially the same radius. That last point deserves a moment. Two stars of very different masses and the same size. To fit a third more mass into the same volume, the pressure deep inside the heavier star must rise very steeply with density. The equation of state cannot soften significantly above nuclear saturation density. Whatever the core contains, it resists compression powerfully. Models that predicted large softening through hyperons or kaon condensates produce stars that should shrink as mass increases. Because the soft interior compresses under the added weight, the observations show the opposite. The radius stays essentially constant as mass grows. Stiffness is required, and stiff equations of state at high density point toward one of two possibilities: either unusually strong nuclear repulsion holding the neutrons apart, or a form of quark matter that is itself stiff rather than soft. The instrument's data, combined with the mass measurements from pulsar timing, has narrowed the radius of a canonical 1 4/10 reference mass neutron star to a corridor centered around 12.5 miles. A decade ago, the uncertainty spanned several miles in either direction. The walls of the corridor are closing. But X-ray timing and radio pulsar masses as precise as they are, study individual stars in isolation. There is another way to learn about neutron stars, one that captures the moment of collision rather than the long, quiet life before it. In August of 2017, that other way arrived. August 17th, 2017, 12 minutes and 41 seconds after noon. Universal time. Detectors on 2 continents registered the arrival of a gravitational wave signal that lasted 100 seconds. The signal was a chirp, a rising tone in the curvature of spacetime, climbing from the lowest frequencies the instruments could detect toward the highest, growing louder and faster as it rose. Gravitational wave signals from black hole mergers are brief, lasting fractions of a second, because massive black holes spiral together quickly. This signal lasted 100 seconds because the objects spiraling together were lighter, a pair of dead stars each close to 1.5 reference masses, circling each other thousands of times per second in the final moments before contact. Sweeping upward through the frequency range, the chirp ended. 1.74 seconds later, a gamma-ray burst arrived at a detector in low Earth orbit. Those gamma rays came from the same direction as the gravitational waves, with a delay consistent with the light travel time through ejected material surrounding the merger site. Gravity had arrived first, and then the fire of electromagnetic radiation followed. That gap of 1.74 seconds tells a story on its own. The gravitational waves travel at the speed of light, like all radiation through empty space. The gamma-ray burst arrived later because it had to punch through the cloud of material being flung outward from the merger before escaping. The jet of high-energy radiation bored through that barrier and continued outward. When it finally cleared the surrounding debris, what reached Earth was a flash of gamma rays carrying energy equivalent to the combined light output of billions of ordinary stars compressed into milliseconds. For that fraction of a second, the merger site outshone entire galaxies in gamma rays from a source 130 million light-years away. Before this event, the connection between neutron star mergers and short gamma-ray bursts was a decades-old hypothesis supported by indirect evidence. After August 17th, it was confirmed. The 2 signals, one in space-time ripples and one in high-energy radiation, had traveled 130 million light-years from the galaxy designated NGC 4993, and they arrived within 2 seconds of each other. The gravitational wave signal itself encodes physics that no other measurement could provide. As the 2 neutron stars spiral close, each one feels the gravity of the other deforming it slightly, stretching it like a pebble near a drain. The amount of stretching depends on the equation of state. Stiff nuclear matter resists deformation. Soft matter yields more easily. The tidal deformability, that readiness to stretch, leaves an imprint on the shape of the gravitational wave chirp in the final moments before merger. Extracting that imprint from the 100-second signal constrained the neutron star radius from a completely independent direction, arriving at a size consistent with the X-ray timing measurements but derived from an entirely different physical effect, measured at the moment of violent death rather than in the long spin of quiet life. The gravitational waves told one story. 12 hours later, telescopes from every continent turned toward the same point in the sky, and what they found there answered a question 70 years old. Gold does not form in the quiet interior of a living star. A star can fuse hydrogen into helium, helium into carbon, carbon into oxygen, and on through silicon to iron. Every element up to iron sits within reach of stellar fusion, given enough time and enough mass. Beyond iron, fusion becomes a net loss, an energy sink. The star cannot push past that boundary by slow cooking. The heavier elements require a different environment entirely. An extreme density of free neutrons, so extreme that nuclei can absorb them faster than they can decay, jumping rapidly across the neutron-rich side of the nuclear chart in the same process traced near the drip line in the laboratory. That process needs neutron densities that a stellar interior never achieves in ordinary nuclear burning. When the two dead stars from the gravitational wave event merged, they tore each other apart. Tidal forces from the orbit shredded the outer layers of both stars as they spiraled inward, flinging ropes of neutron-rich material outward at a fraction of the speed of light. In that expanding cloud of dense ejecta, the rapid neutron capture process ran at full speed. Nuclei in the ejected material absorbed neutrons one after another, barely decaying between captures, threading along the neutron-rich corridor near the drip line, building upward through the heavy elements. The glow that followed in the days after the merger changed color as the ejecta expanded and cooled. Early optical emission came from lighter R-process products near the first and second peaks of the heavy element distribution. Over subsequent days, the light shifted redder and infrared, driven by the opacity of heavier lanthanide elements with their dense clouds of electron transitions. The color sequence matched the expected signature of R-process nucleosynthesis, producing material deep into the third peak, elements with mass numbers near 195. One element was identified directly in the spectra. Strontium, element 38, freshly made in the neutron-rich ejecta, showed its spectral fingerprint within days of the merger. It was the first time a newly produced R-process element had been directly observed in the act of being made. Gold produced in that single merger event amounted to roughly 10 times the mass of this planet. Platinum, in comparable quantities. Europium, neodymium, uranium, heavier elements across the lanthanide and actinide series, all forged in seconds. Crucially, that outpouring of heavy elements came from multiple sources within the same event. Rapid neutron capture did not run only in the dynamical ejecta, the material torn off the stars as they spiraled together. An accretion disk formed around the remnant in the first second after merger, and neutrino-driven winds from that disk drove additional material outward over the following seconds. Multiple separate outflows, each with different neutron richness, each tracing a slightly different path through the nuclear chart, combined in the expanding cloud. The full kilonova was the sum of all of them, and the diversity of elements produced reflected the diversity of conditions in which the R process ran. The heavy element abundances in the universe carry the fingerprint of exactly this mixture, preserved in the spectra of old stars formed from the ejecta of ancient mergers. The ring question from the very beginning of this story has its answer. The gold is there because two dead stars, each containing close to 3 × 10 to the 57th stacked neutrons, collided after billions of years of orbital decay. The heavy elements in the universe required the neutron star to exist close to its limit. But what happened to the neutron stars themselves after the collision is where the story takes its final, strangest turn. Two neutron stars colliding carry angular momentum from their orbital in spiral, and the merger does not stop at the moment of contact. The two dense objects smash together and form a single remnant that is hot, rapidly rotating, and, depending on the combined mass, potentially larger than anything the universe's physical laws are supposed to allow. The combined mass of the merger event was about 2 74/100 reference stellar masses. The Tolman-Oppenheimer-Volkoff limit sits somewhere between 2 and 2.5. Their sum exceeded the limit, or at least approached it closely enough that no stable, non-rotating neutron star could hold the mass without collapsing. For a fraction of a second, something existed anyway. Picture what this object actually is. A sphere of nuclear matter larger than a city, now distorted into a flattened, rapidly spinning shape by the combined angular momentum of two in-spiraling stars. The outer layers rotate at one speed. The inner layers rotate faster, dragging the material between them into shear flows no material on Earth could survive for even an instant. The temperature inside has spiked to conditions that have not existed anywhere in the universe since the first second after its birth. Magnetic field lines from two separate stellar remnants have been wound and tangled into a chaotic braid, the total field strength hundreds of billions of times that of any laboratory magnet. Neutrinos stream from the surface in a torrent that carries away energy by the octillions of joules per second. The object is violently unstable along multiple physical dimensions simultaneously, held together by one thing only. A hypermassive neutron star is supported by differential rotation. The inner layers spin faster than the outer ones, and the centrifugal force from that differential adds a structural support that ordinary pressure cannot provide. The mass sits above the limit, alive on borrowed time, stable only because the rotating shape of the object provides an additional pressure that a non-spinning version of itself could never sustain. The borrowed time has an expiration. Angular momentum leaks away through viscosity, through magnetic field interactions, through the emission of low-level gravitational waves. As the differential rotation slows, the centrifugal support fades. The object contracts. The pressure required to hold the remaining mass rises. The Tolman-Oppenheimer-Volkoff feedback loop closes in. Calculations place the remnant's lifetime somewhere between a fraction of a second and a few seconds before the rotational support failed. Gravitational wave observatories that detected the inspiral were not sensitive enough at the kilohertz frequencies that would have revealed the remnant's oscillations. That signal, the ringdown of a spinning blob of matter more massive than the limit, carrying direct information about the equation of state at its most extreme, arrived at Earth and passed through undetected. That gap in the data is not permanent. Third-generation gravitational wave detectors planned for construction in the 2030s are expected to reach the sensitivity needed to detect post-merger ringdowns routinely. Each one they record will carry a frequency signature encoding the equation of state at the densities that no other probe can reach. The hypermassive remnant of the merger event of August 2017 collapsed. When it did, the borrowed time ran out in a span shorter than a blink. When the differential rotation of the hypermassive remnant slows below a critical threshold, the balance between gravity and pressure tips irreversibly. Gravity gains ground. The star contracts. Contraction compresses the already extreme interior further, which in ordinary dense matter would raise the pressure. But the relativistic pressure-gravity feedback, described in the chapters on the Tolman-Oppenheimer-Volkoff equation, ensures that in this regime, raising the pressure also raises the gravity in proportion. The fall accelerates. The surface of the collapsing object falls inward at a significant fraction of the speed of light. The radius shrinks. Within roughly 1 millisecond from the onset of instability, the surface crosses a critical threshold, the point at which the object's gravity is strong enough that even light cannot escape from the surface. The Schwarzschild radius, for an object of 3 or more reference stellar masses, is a sphere with a radius of a few miles. Safely inside the 12-mile sphere, the neutron star occupied before the collapse began. An event horizon forms. Below it, no signal, no particle, no electromagnetic wave, no gravitational wave can reach the outside universe. The object becomes a black hole. Consider what this means for the matter that was, a millisecond earlier, the structured layers of a neutron star. The nuclear pasta in the crust, compressed by the collapse, shears and fragments as the radius shrinks below anything it was designed by physics to tolerate. The superfluid neutrons in the outer core, which had been circulating in persistent vortices since the star first formed, carry their angular momentum inward as the radius contracts. The spin rate climbs as the radius falls. The tidal forces inside the collapsing object reach magnitudes that would tear atoms apart millions of times over. In a fraction of a second, the entire internal structure of 2 neutron stars, built across billions of years and studied from afar by every instrument civilization has pointed at the sky, is erased. From the outside, the transition is effectively instantaneous. One moment, a dense, violently oscillating blob of nuclear matter. The next moment, a black hole of roughly the same mass, retaining only mass, charge, and angular momentum as externally observable quantities. The texture of the matter that fell in, the quantum states of each neutron, the magnetic field threading through the crust, the superfluid vortices in the outer core, the possible color superconducting phase in the inner core, all of it vanishes from the accessible universe. Classical general relativity offers no mechanism for retrieving that information. Quantum field theory, however, makes a troubling prediction. A black hole radiates incredibly slowly over timescales that dwarf the current age of the universe by many powers of 10. The horizon emits thermal radiation as a consequence of quantum effects at its edge. Whether this extraordinarily slow process eventually returns the information of everything that fell in, encoded in subtle correlations in the outgoing radiation, or whether that information is genuinely and permanently erased, is one of the most fiercely contested problems in theoretical physics. The argument touches every major framework of quantum gravity that has been proposed. None of them has settled it conclusively. The 3 to 4 times 10 to the 57th neutrons that crossed the horizon are, in a real sense, still the subject of an active argument about the nature of reality itself. Whatever the ultimate answer, from the perspective of the universe, outside the horizon, the collapse is complete. What happens to them on the other side of the event horizon is a question that classical physics can answer in one limited way, and quantum gravity cannot yet answer at all. Inside a black hole, the concept of neutron matter becomes undefined. From the perspective of an observer outside the horizon, the neutrons are simply gone. The black hole retains a total mass, a total charge, and a total spin. Every other property of the material that created it is hidden. There is no way to ask from the outside whether the interior contains neutrons or quarks or some exotic phase, because the interior is causally disconnected from every measurement anyone can make. Classical general relativity makes a prediction about the interior. It predicts that the collapsed material continues to fall inward, the density continuing to rise without limit, the tidal forces on any object inside growing without bound as the radius shrinks towards zero. The mathematics of general relativity, applied without modification to the interior, arrives at a singularity, a point of infinite density where the curvature of spacetime itself becomes infinite and the equations cease to produce finite answers. Physicists generally read a physical infinity in an equation as a signal that the equation has been taken outside its domain of validity. The singularity at the center of a black hole is widely understood as evidence that general relativity fails at scales small enough for quantum effects to dominate. A regime called quantum gravity. At those scales, a theory of gravity that incorporates quantum mechanics would produce finite physical results. The singularity would be replaced by something describable, something real, possibly something structured. No such theory exists in complete, usable form. String theory, loop quantum gravity, and other approaches each provide partial answers in limited regimes, but none of them can be applied straightforwardly to calculate what happens at the center of a collapsing stellar remnant. The question of what the matter becomes inside a black hole is genuinely open, sitting at the intersection of the two most successful theories in physics, neither of which works in that regime. There is a related strangeness worth naming. A black hole is described externally by just 3 numbers: its mass, its electric charge, and its rotation rate. Every other piece of information about the object that formed it is invisible from the outside. 2 black holes of the same mass, charge, and spin are physically indistinguishable regardless of whether one was made from a neutron star and the other from a cloud of hydrogen gas. The specific arrangement of 3 times 10 to the 57th neutrons, their individual quantum states, the exotic phase of matter they inhabited at the center of the original star, all of it is compressed into 3 numbers and nothing else. The universe, at a horizon, becomes strikingly simple. The neutrons that crossed the horizon carried with them the record of everything from the opening chapter to this one, from the drip line in a nuclear physics laboratory, where a handful of them leaked from an atom in a fraction of a second, to the 3 reference masses stacked by gravity that no nuclear force could have bound. The entire arc of the story crosses the horizon with them. Whatever they become on the other side, the question asked at the beginning of this video has reached its outermost limit, but there is one more strangeness before the answer is complete. Because in the catalogue of every compact object ever measured, a suspicious gap exists between the heaviest neutron stars and the lightest black holes, and something may be hiding in it. Between the heaviest confirmed neutron stars and the lightest confirmed black holes, the compact object catalogue contains almost nothing. The 3 massive pulsars measured through Shapiro delay timing cluster below about 2.5 reference stellar masses. Black holes identified through X-ray binary systems, where the compact object feeds on a normal stellar companion and betrays itself through the spectrum and dynamics of the accretion flow, rarely fall below 5 reference stellar masses. From roughly 2.5 to 5, the catalogue is nearly empty. This emptiness has a name. Researchers call it the mass gap, and it raises 2 distinct possibilities. The gap may be real. The physical processes that produce neutron stars and the physical processes that produce black holes may simply not produce objects in that mass range very often. The explosion dynamics of massive stellar cores, the conditions that determine whether a collapsing star produces a neutron star remnant or falls directly into a black hole, may create a natural scarcity of intermediate masses. Or the gap may be an artifact of how compact objects are detected. X-ray binary observations are biased towards systems that have accretion disks bright enough to see, and the disk luminosity depends on the mass transfer rate, which depends on the orbital configuration, which is not a random sample of all compact objects in the galaxy. A gravitational wave event detected in 2019 addressed the gap directly. 2 objects merged. One was a black hole of roughly 23 reference stellar masses. The other was about 2 6/10. The smaller object fell squarely in the mass gap, too massive for a standard neutron star by most theoretical estimates, too light for a black hole by the standards of X-ray astronomy. Its nature remains contested. A very massive neutron star near or above the Tolman-Oppenheimer-Volkoff limit, a very light black hole formed by an unusual collapse, or something in between, are all on the table. The gravitational wave event provided limited diagnostic information because the signal was dominated by the mass ratio between the 2 objects, and no post-merger signal was detected. Distinguishing a massive neutron star from a light black hole in the mass gap requires tidal deformability measurements, and for an unequal mass merger, the smaller object's tidal signature is suppressed. As the gravitational wave detector network improves its sensitivity, the rate of detected mergers will climb. Among those detections, some will capture equal mass pairs near the mass gap boundary. Their tidal signatures will be measurable. The boundary between the last neutron star and the first black hole, which determines the true Tolman-Oppenheimer-Volkoff limit, will be traced from the gravitational wave side rather than the pulsar timing side. The gravitational wave detectors currently operating have already confirmed multiple neutron star mergers and black hole mergers. Future upgrades will reach greater sensitivity. Each merger detected near the mass gap boundary will add a data point to the diagram that theoretical astrophysics has been drawing for decades. Mass on one axis, compactness on the other, with the Tolman-Oppenheimer-Volkoff limit drawn as a vertical line whose exact position is still being located. Every new measurement either confirms the line where it was estimated or forces it to move. The most recent data has kept it consistent with 2 to 2.5 reference stellar masses, which is itself a constraint on the nuclear physics inside every neutron star that has ever existed. The gap is closing, and as it closes, the other path to collapse, slower and quieter, deserves its moment. Some neutron stars reach above the Tolman-Oppenheimer-Volkoff limit without a merger. They arrive there through a lifetime of spinning. A uniformly rotating neutron star can support more mass than a non-rotating one, because the centrifugal force of its spin pushes outward against the inward pull of gravity. For the fastest spinning neutron stars, those rotating several hundred times per second, the additional support from rotation allows them to carry up to about 20% more mass than the Tolman-Oppenheimer-Volkoff equation predicts for a stationary star. An object that would collapse immediately if held still survives because it is spinning fast enough. Astronomers call these objects supermassive neutron stars to distinguish them from the short-lived hypermassive remnants of mergers, which rely on differential rotation rather than uniform spin. A supermassive star rotates as a solid object, all parts spinning at the same rate, the centrifugal force simply adding to the pressure budget as a whole body effect. The survival is real but not permanent. Rotating neutron stars radiate energy. A spinning magnetic dipole loses energy continuously by accelerating charged particles and emitting electromagnetic radiation. Over millions of years, that energy loss slows the star down. The rotation rate decreases gradually, second by second, year by year, across geological timescales. The centrifugal support diminishes in proportion. Eventually, the star's spin rate drops below the threshold required to support its mass. At that moment, the star crosses the Tolman-Oppenheimer-Volkoff limit for the first time, as if it had simply grown heavier without actually gaining mass. There is no gradual adjustment. The support evaporates and the instability is immediate. Collapse follows in milliseconds. Some researchers have proposed that a class of mysterious radio signals might be the electromagnetic signature of exactly this event. Fast radio bursts are millisecond duration flashes of radio waves arriving from cosmological distances, energetic enough to be detectable across billions of light-years. Repeating in some sources and appearing only once in others, the source mechanism producing at least some of them remains debated. A collapsing supermassive neutron star, converting its entire remaining rotational energy into electromagnetic radiation as it crosses the limit, would produce a burst of energy on roughly the right timescale from a source that would leave no stable remnant behind, only a black hole and a flash of radio waves. The non-repeating class of fast radio bursts fits this picture. A one-time event, no recurring source, carrying the energy of a star's final spin. Whether this is the correct explanation has not been confirmed. The signals are real. Their origin continues to be traced back through the universe. Every answer unlocked reveals another question waiting behind it. There is something quietly remarkable about the supramassive neutron star scenario. If it is correct, then somewhere in the galaxy right now, there are neutron stars spinning down toward a threshold they cannot survive, objects that appear to all observations as ordinary radio pulsars for millions of years and then simply stop. Their collapse would leave a black hole and nothing else, no supernova shockwave, no visible explosion, no ejected material, no kilonova. The galaxy would gain a small black hole without anyone noticing. How many of these quiet transitions have already happened in the Milky Way's history is completely unknown. The universe may be filling the mass gap with black holes produced in silence, one collapsing supermassive pulsar at a time. And now all the pieces are assembled. The central question asked at the very beginning of this story has everything it needs for an answer. Everything in this story has been building toward one number, and the number itself is not what matters most about it. Return to the gold ring from the first chapter. A piece of jewelry small enough to fit on a finger. Ordinary in appearance, extraordinary in origin. The gold atoms in that ring trace their history to a collision that happened before this star system formed, somewhere in the Milky Way, between two objects that each spent billions of years circling each other as they bled angular momentum into gravitational waves. Each of those objects was a neutron star, each one held, in its 12 miles of compressed matter, somewhere around 2 to 3 times 10 to the 57th neutrons stacked by gravity in a sphere no wider than a small city. In a nucleus, the answer to how many neutrons you can stack is a few dozen to a few hundred, depending on the element. The drip line sets the hard ceiling, and beyond it, the strong nuclear force gives up. No further binding is possible. The nucleus dissolves. Gravity does what the strong force cannot. It stacks neutrons in quantities that exceed anything a nucleus can hold by 56 orders of magnitude. 2 times 10 to the 57th for a typical neutron star, 3 or 4 times 10 to the 57th for the most massive ones. At some point, even gravity finds its limit. The Tolman-Oppenheimer-Volkoff equation tells us somewhere between 2 and 2.5 reference stellar masses. Beyond that threshold, no force in nature can hold the stack together. Neutron degeneracy pressure fails because relativistic neutrons carry pressure that adds to the gravity it is trying to overcome. Quark matter provides stiffness but cannot break the relativistic feedback loop. Rotation buys time but not permanence. When the limit is crossed, the stack collapses. The physics running out of options at that boundary is a fundamental feature of general relativity, built into the structure of curved spacetime by mathematics that admits no exceptions. Spacetime itself enforces the limit. In a universe with different constants, the limit might fall somewhere else. In this one, it falls where it does, and the neutron star merges it produces. Scatter their R-process products across the galaxy, and some of those products eventually cool and condense into rocky planets orbiting young stars, and some of them end up in rings worn on fingers. The gold exists because physics works as close to its own breaking point as nature allows, then breaks on schedule. We do not know the precise value of the Tolman-Oppenheimer-Volkoff limit. We are closing in on it from every direction simultaneously, from pulsar masses measured in radio timing, from radii measured in X-ray pulse profiles, from tidal deformabilities read from gravitational wave chirps, from the mass gap traced by mergers. Each new measurement eliminates more theoretical possibilities. The corridor is narrowing. When the exact number is finally pinned down, it will tell us what matter is made of at conditions no laboratory has ever reached and no equation has yet solved. It will tell us whether quarks pair into exotic superconducting phases deep inside the densest stable objects in the universe. It will trace the precise path along which gold was forged across cosmic time. The question was never really about stacking. It was always about how far reality can be pressed before it stops being reality. And the answer, written in every neutron star still spinning in the dark, is that the universe allows exactly as much as the mathematics of curved spacetime permits. The gold in that ring carries the proof. 2 stars lived for billions of years right at that boundary, collapsed through it on schedule, and handed us their heaviest elements in a flash of light. Reality broke exactly where it was supposed to. The atoms on your finger are the receipt,